запись.
Дзен, ты можешь сделать full screen?
Да, сейчас сделаю. Okay, done? Okay, hello guys. Today is... привет. Today is lecture number 19, numbers and names, living math. Okay, what about the previous ones? Do you have any questions for the exercises?
No, we did all of them.
Huh?
We did all of the ones we did.
You did all?
Yeah.
Everything is okay?
The missing one was the infinite dimensional cube.
It's just to a circle. A sphere. Yeah, that's the weird part.
A sphere?
Yeah.
You mean this picture?
Yeah.
Ah, you've seen it, right? Okay, yes, it is 15 dimensions. Cube.
Yeah.
But it is about projection. There are different projections. This is one type of the projection. Maybe this way or that way, yes, but it looks like that. Agree.
We figured it out without Google.
Okay, good.
Through reflection and introspection.
Okay, good guys. Okay, reflection, introspection via Google, but without it. Okay.
No, we did not use Google. We used Google to verify, and we were very happy that we were correct.
Okay, guys. Okay, the theme today is living math. Living math. So we were talking about mathematics like symbolical, right? But there's also another type of mathematics, actually different types. One of these types was language. Remember this dial language that we were talking about? Mathematics is just one dialect of this language.
Question.
Yes, question?
How does language... I didn't really get how language has to do with math. I don't really get it.
Okay.
Math
Mathematics is a language. That's what it's to do. Mathematics is a language. You can use mathematics actually to describe anything. You can, but just this language, like mathematical language, is not really suitable for certain people stuff. You know, it's difficult to. You cannot talk mathematics. You can write it symbolically, right? Like we do, like all the scientists do. It's very useful. It's universal and everything. But it's difficult to talk mathematics, right? So that's why it was invented or discovered, whatever you say. It probably is discovered more useful word for this. So it was discovered language that is more useful for people, right? And it's more useful from the way of using oppositions and everything, because our life is actually combined of oppositions. So, and it's useful both for people and for computers and for whatever, right? And for mathematics, written and spoken. Regular mathematics is just written, symbolical, and more useful for numbers, because it started and developing from numbers. Now it's not about numbers, mostly about these, operators, symbolical things, groups, symmetries. This modern mathematics is about it. So-called categories, it's about more generalization of these concepts. So it is more than numbers, but because it's grown up from the numbers, it's very close connected to them. So it's a language, yes. But still written language, All modern mathematics is written language, right? But there is also another type of mathematics, which is actually living, much more than even language. And this is any clue what can it be? The mathematics in like reality of mathematics.
That's what it's like what we do in what math is in real life. What math is in like
Physics.
Yeah.
Physics is using mathematics actually. Somehow, yeah, it's correct, yes. But actually, I'm talking about something that people do. People created it.
No. What do you do right now with data?
Talk. We do math.
Yeah, you talk.
We talk.
Right? English.
Yes, language. Yes, language. Each language actually has mathematic background. Yes, it has. But it's if you try to use like English or Russian or any other language to write equations, right? You will see very easily that it become very bulky. It's very difficult to use. You can talk, but to write it and to use it as symbolical language like mathematics is used, it's very difficult. That's why we use mathematics. So mathematics is good in one thing. Languages are different. Are used in another thing and useful in other fields. Dial language is used in both fields, but it is the future. It's not yet a common language. But we have some mathematics which is really living thing, and we're using it. It's a very useful thing. So any clue what is it? Hmm?
Is it like Papa said, you basically math is everywhere basically. It's like
Yes, you're right. You're right, Katya. You're totally right. Yes, it is everywhere. You can apply mathematics everywhere, right? And it's, in a certain way, it is everywhere. Yes, but there is a particular thing that's very close to mathematics, and at the same time, it's very alive, sort of.
Music.
Music again, yes. Music is actually considered a dialect of Dial language, and we had some parts of music translated, and both from music to Russian and back, and we have to mathematics. We have different stuff. I even translated part of human genome, one of human genes. Yes.
What's DL?
Dial is language that we're talking about. This universal language. Remember?
Oh.
Yeah. Okay. So you're out of clues. Okay. Okay. This I'm talking about computing. Living math. Computing is, yes, it's part of nature, but we use this process, physical and other processes, because there are different types of computers. Computers can be made not only on electronics like it's now. The first computer was created in Britain. It was Charles Babbage. It was mechanical, totally mechanical. Some wheels, some other things. There are computers that are made of, believe it or not, on like whistles, sort of. There's air, yeah, sort of types of whistles. The air goes through the pipes, and interacts with each other. They're pretty useful computers, pretty easy to do in certain simple operations. They actually even used in industry, maybe even now, but they were used at least, not long ago. So computers may be made of different things, not only electronics. There are computers based on photonic things like photons and everything. But basically computers, I would not talk about like how computers are made right now, but mostly they're based on numbers. And but interesting enough that just well at the background of any computer is this some count, 1 plus 1 plus or minus 1, that kind of numbers, operations with numbers, right? Still interesting enough that starting with numbers and goes further and further up, making more and more complex construction out of numbers. We can construct vectors, we construct functions, we can construct more things, even categories, and then we can even come to common language. And actually modern computers can speak pretty roughly, but can speak natural languages, can understand natural languages and everything. But interesting enough that, so first of all, why it's possible? Why it is possible? Because of universality. Everything is universal, and numbers are as universal and as words or whatever else. So we can use numbers to explain anything in the world. That's what we do in regular computing. But the modern computing went much further. For today, there was an event that was published, I think, December previous year, 2019. And this event was some achievement made by Google computer, which have 53 quantum elements called qubits. 53.
I know what qubits are.
Okay. We are not we're not going that deep into qubits. Qubits is a quantum element. First of all, it's a generalization on quantum base of the term of bit. But anyway, what is needed, what is important for us, that there are only 53 qubits there, and this computer, after working about 200 seconds, right, it solved some mathematical problem or arithmetical problem called with connected with this encryption things, encryption, decryption. And for this 200 seconds, he made a job that for the most powerful modern computer, which is called Summit, will take about 10 million years to do the same job.
Oh, wow.
Summit is the fastest modern supercomputer, fastest and most powerful. It makes about 2 so-called exaflops. So just elementary operations. It means 2 10 to 19 operations per second. So 10 with the 18 zeros after that. So that's the speed.
Operations.
Operations.
Like addition or subtraction.
Yeah.
Oh God.
10 to with 18 numbered, with 18 zeros after 10, right? So it's very fast, very powerful, but it will take 10 million years for this computer to do the same job which this computer, Google, has done for 200 seconds.
So it only worked for 200 seconds.
Yeah. For 200 seconds he solved the problem of encryption, which will take Summit for 10 million years, that's calculated. So it's impossible to do by Summit because we don't have this million years, right? That's for sure. So that event was called demonstration of so-called quantum supremacy. So the quantum computers are so powerful that they can overpower any regular normal computer based on regular numbers. Because quantum computer works really differently, and that's why I'm going to talk now. By the way, there are 53 qubits, right? But the biggest quantum computer for now has about 10,000 qubits.
Whoa!
Just to understand.
How long did it run for?
And it runs for military, for United States military. It's called, if I'm not mistaken, Sycamore, I think. Oh, I forgot the name for this. I forgot the name. For 10,000 qubits, right? And which is important, I'll explain later. Each qubit has just 15 links, 15 connections with other qubits. 15.
What are qubits?
Remember? Yeah, qubit is just quantum element. Like we have, like in regular computer, we have transistors. Maybe you heard this name. Each chip has trillions, like big chip has trillions of these transistors. And in quantum computer we have these qubits. They are made of different stuff, different physical things are used to it. I will talk about a little just in a moment, okay?
What do the qubits do?
No, what is bit? Bit.
That's
Bit?
my favorite. Well, I'll explain to you later.
Yeah, I'll explain.
Oh, Jada can explain. Okay.
Yeah, I'm going to talk about this. So a regular bit, how it is implemented in physical system, any physical system, usually on some sort of transistor or whatever. It's a physical system that has two positions, like certain simple switch. Actually, the general element of modern computers are actually some sort of switch. So switch has two positions, on and off, right? Which is usually denoted off by 0 and on by 1. So it's binary system, 0 and 1.
Can I explain a qubit?
Yeah, just wait. Wait. This is bit. So any kind of switch, whatever you have switch. Switch can be transistor. Switch can be like your kitchen faucet, you know? You have this crank, right? So water going, water is on, or water is off. This is a switch. and this is a bit system. Bit is 0 or 1. So this is the basis of any modern computer, except quantum. And actually, whatever big computer, modern computer is just a lot of such faucets, you know, connected to each other in many, many different ways. That's all. Just switches connected to lots of things. This is normal computer. Now about qubit. Quantum system, like quanta, any quanta, right? It's like elementary particle, like electron particle. It is a quanta. All elementary particles are quanta. So one quantum is like electron, right? Electron, it seems that it can have the same thing like switch, two positions. It is called spin up and spin down. Spin, it is a so-called rotation momentum. So it's spinning, right? Electron spinning. Spin up is like this. Spin down is like this. So it's different rotation. Up and down. So it looks like classical thing, right? So maybe we can think that this is a bit, right? Up or down. Maybe down is 0, up and 1. Up is 1, right? Looks like that. But interesting thing about quanta, which is all quantum mechanics about, that there are no this so-called plane states, 1 and 0. Each state is actually a mixture of both, all the time. All the time. And when you try to measure it, it will be measured like a mixture. So sometimes you get 1, sometimes you get 0. And how much 1 or 0, it's called probability. So probability 1 or probability 0. Two probabilities. And they are different in different situations. So it's a very complex thing. So even the simplest thing in physics, like quanta, there's nothing simpler than that. It has not two positions. It looks like it should have, but it doesn't. It has a mixture of both. They're always time mixed. Like there was a famous idea based on that. It was in the beginning of quantum mechanics. There was a guy who was his name is Schrödinger, and probably you maybe even read about it. He invented some sort of a thought experiment with a cat. So Schrödinger's cat, which has two positions. Is he alive or dead, right?
Oh God.
No, it's easy. Alive or dead, right? So dead is 0, alive is 1, right? But the cat of Schrödinger, he not alive and not dead. He is always in the mixture.
How?
And nobody can explain. And maybe I can, but not today. But so the interesting thing, that's sort of a paradox. You can think for now it is a paradox, right? It's a paradoxical thing. So it's a mix between alive and dead. So quantum mechanics is always about this mix. Everything is mixed. Spin up, spin down, energy, momentum, whatever you have, it is mixed. And qubit is exactly that. Qubit is a quantum element, like electron or whatever, like photon, any particle, or some quantum states, some quantum devices. Like Schrödinger cat can be a qubit, if we really construct, if we do that in hard, hard metal, whatever. If you create cat like Schrödinger suggested, right, he will be a qubit, or it will be a qubit. So qubit may be different things. Usually there are certain quanta. And to work with this, it's not enough to have one quanta. It's not enough. This quanta should be so-called entangled. And entangled this this term means that elements, these qubits, right? It could be electrons or photons or whatever, right? They should be connected with each other in quantum way. Connected very serious quantum way. One of these types of connections called BEC, it's Bose-Einstein condensate. It is a special type of matter that never existed before. These Bose condensates were actually discovered in 1911, but people didn't know that they are those. And then when people found out what is it, was a long story. For 100 years, actually, people were trying to understand what is this BEC. But in this condensate, these particles behave like they are one. It's just like one particle. And this one particle, it presents itself like there are many of them. It's a very paradoxical thing. It's a paradox. It's a paradox, living, real paradox. And in this way, when they're behaving like this, we look at them, we register many particles, but in reality it's just only one. And each of these particles can have this, this spins up or down or mixture, of this, right? Looks like they are separate, but actually it's one particle, which is one of these things, and it displays itself in these different ways. So the whole idea of this quantum computing is how to work with such a strange media, such a strange, condensate, this kind of matter. It's a new type of matter, new. It's not solid, not liquid, not vapor, not gas, not even plasma. This is something very special.
Oh.
Yeah, and physicists are really working with this now for a long time. So, and we have this quantum computer which make these particles so-called entangled. Some of them are worked with real Bose-Einstein condensates. Some of them are differently entangled. There are different types of entanglement, right? But again, in each type of entanglement, particles works like one, like it is one thing, which displays itself in different ways. Like there are many. So remember, we were talking about this paradox one many. Remember?
Yeah.
Did you try to? If you try to make a paradox out of it, this is one of these physical examples. That's like real examples of one many. BEC, it is this paradox alive. Paradox alive. And now what we're going to do. This is a little, this paradox difficult to understand, of course, but I just explain a little how it all works, basing on what we learned to this moment. And we start from a little different stuff, but you will remember. Like, let's talk about some plane, right? Plane, 2D plane, two-dimensional plane, right? Like, this is like plane, right? And we put, on this plane, we put a coordinate grid, right? So, X and Y, right? On this plane. And these are coordinates. Like we may make a grid here, like this. Understand, right, what I'm doing? These are coordinates, just a grid on this plane.
Uh-huh.
X and Y, 2D, 2 dimensions. And this is flat, so no curvature. This is flat space, flat two-dimensional space. Now let's think that this space is like actually made of rubber, right? And we push from down there. What will have this? And we will have something like this, right?
Yeah, a bit higher.
Right, when we're pushing from here, right? And what will happen with these lines, with this grid?
The curve. Yeah, they'll
Yeah, they're curved, yes. They go like this, right?
Yeah. That reminds me of when this reminds me of a real life thing when the top part is water and then the bottom part is the after effect of when a raindrop hits it.
Yep. So you understand, this is a curvature, and this thing is called curvature. This is curved space, right? Curved space. Now let's look here. We have, remember, these basis vectors, right? Basis vectors like EY and EX. Two vectors of basis, right? This and this for x axis and y axis, right? Here we have this. This is like a regular square, right? Each here is regular square, but here when we push this rubber, the square is deformed. Like if we look here, right, we will see square here like this. This is EX and this is EY, right? So the angle between them would be not right angle already. Here is right angle. And here maybe not, because it's all curved, all deformed, right? The length of this is not a square already. This is very deformed thing. If you look like from up there, from that way, right? We will see not a grid, not a regular grid, but something like this.
Oh yeah, that's actually really good.
Right? If you look from here, right? Something like this. So this is very, very curved. It's not a square anymore. This is some deformed thing. So the vectors changed, angle changed, everything has been changed. And mathematically, this change is actually written like this. If you have vector, like each vector, like for example, A with the index I, right? So we how to do it like B. If you work with the matrices, remember, this is a matrix.
Transformation matrix.
And this is another vector. So each vector is changed to that vector with the use of a matrix. So matrices are used to actually to show how the vectors are changing in these cases, right?
Can I ask a question here?
Yes, sure.
I'm actually curious.
Mm-hmm.
If there was a creature, some flat creature living in the picture above,
Mm-hmm.
and then that flat thing got stretched, to the creature it should be completely transparent because the creature itself got stretched, and the laws of physics and the light, everything just, it is to the outside observer that the stretching did happen, right?
Not only with the observers here on the plane itself, something will happen too, because you may be here, you're deformed, right?
So yeah, it could be 90 degrees, that's right there.
No, you are deformed. But if you're here, right, far from this push of this force, yeah, right, pushing, if you're here, you still have your regular square, right? So in relation to you, this thing is changed. So you can see something, and actually that's what we're doing. I will tell you just in a moment, okay? So in reality, probably you've been in the Science Museum, right? So you know that curved spaces actually is the cause of gravity.
Yeah.
So gravity, it is a distortion of space-time.
Yeah.
And distortions usually can be seen here. Like usually, like light goes in the shortest way, right? Mm-hmm. This is straight line. Straight line, right? Straight. So if you put here, like for example, some light will go like here. Straight, right? But if you put light here, what will happen? It will go again, it will take the shortest way, but the shortest way will not be a straight line anymore. It will be something like this, again, it's curved. And that's what happens in our space-time.
Right, but the light is curved.
Uh-huh.
So to you, all the distortions look straight because the light curves as well.
No, it may be curved pretty much. Like for example, in our case, right? It curved that light goes can go even on orbit of a certain star. Like for example, like black hole can be orbited by light. The light is curved like this. It goes to the orbit of the black hole. It's orbiting. There's also light orbits around black holes.
Something crossed my mind.
Yes.
I just realized that if the flat grid could be gravity, and the dip right there could be
A planet or black hole.
yeah. It could be a planet, and from above, that large curve in the middle could be the planet.
And it was what curve in the middle?
The greater it curves, the gravity.
Yeah, exactly. No, what Viti is saying is that that curve, the distortion,
Mhm.
Viti is saying that in the center you could think of it as a black hole that's doing that distortion.
Oh, you mean for the planet?
Yeah.
Or planet, yeah,
The bigger the mass and density, the bigger the dip.
exactly.
Yeah. But actually, there is a theory that each quantum is a sort of a small black hole. It is in a matter of fact, it is something like this, a little more complex, but very close to that. So the matter is a bunch of small, not black holes, but something like this. It's called horizons, right? The black hole actually it is a horizon, but the idea is not that far, not that far from reality. So now what I also just want to repeat that you see this basis is changed, and it's changed differently. Here it's maybe far from right angle, but here far from for the force, far from distortion, right? It's almost the same as was here, right? It was not changed here, but here it's changed. So in different places the basis is different. So this thing depends on this B depends on coordinates x, y, z, and t in space-time, right? So it is a function of coordinates and time. This B, this matrix, become a function. So it is called local symmetry. This is the term that you maybe better to remember. It's called local symmetry. The symmetries that we talked before, they're called global. They everywhere are the same. But with the local symmetry, in one point of space, there's rotation to one angle, in another angle. There distortion is different. There can be the scale, the scale pulled or squeezed in different ways, in different directions. So it depends upon point in space and time. Okay. So now we go a little further to these things. Okay, so local. Local means dependent on space-time, dependent on point of space-time. Local symmetry. Now, okay. Let's look at distorted space-time, right? A little. For example, like this, right? You may notice that for this point, right? For this point, even the length, each length to the second to this position, the lengths are different. When this space is distorted, right? Like a pull, like the things are pulled in both directions, like the length will increase here and increase here. Here increase too. In some place it may squeeze, so the lengths may become smaller and everything like this. So for each point in space or in space-time, the distances to the closest points are different. They become different. When it's no curvature, the lengths are the same. And the length there's a term called metric. And metric, it is exactly the function that shows what is the distance between the closest points in space or space-time. Just the distance between them, right? So, and when it's distorted, the distances are different. And when distances are different, of course, you may think that like interaction between points, like with this point and this point, may be different too. They interact with, in physics, close points, they interact to each other, right? So they can affect the movement of one point, can affect movement of another point. But when they are distant from each other, they do not really affect each other when they are really distant. Like for a point here and point here, they are too far. Point here and point here are closer. Point here are very close, probably they, or maybe even the same. So they affect each other in a very hard way. So the distance actually displays not only like distance that we know it, but also the like the relative effect on the closest point. Distance describes this, so the effect, physical effect or whatever. The mathematics for this was developed by German guy, Bernhard Riemann, and he was like 27 years old. He was a student of another big mathematician, Carl Gauss, and Gauss asked him to think about these geometrical questions like curvatures and whatever, because Gauss himself, maybe you remember, I think I told you that Gauss actually he discovered the curvature in his mind, right? He discovered that it can be possible, and he even tried to measure angles of the triangle on the tops of 3 mountains. So he climbed 3 mountains with his friend, and they tried to measure the angles between this triangle, right? On the tops, on the summits of 3 mountains. And some of these angles are is it 180 or more or less. So Gauss measured this, but he never published it. So he asked Riemann.
In his case, actually, it was 180, right?
Yes. He didn't find anything except 180. He said that the geometry is Euclidean, right? But he had it in his mind, so he talked to his student Bernhard Riemann, and Riemann for 1 year he developed the whole mathematics, which is very famous now, and this is the mathematics of Riemann geometry. And I spoke about this a little, right? Riemann geometry, which is very different from Euclidean geometry. And the main thing there, it is so-called tensor. It's called Riemann curvature tensor. This looks like this. Actually, it is a matrix, but you see there are 4 indexes here, not 2. Like vector has 1 index, right? Matrix has 2 indexes. There are 4 indexes. So you can think about it like four-dimensional hypercube table. Each index is a dimension. So table of like 3-dimensional cube is table like this, right? Numbers here everywhere in the cube. And 40 is a 40 cube. So this is Riemann tensor. And further, Einstein used this tensor to create the general theory of relativity. And actually he's shown that the curvature is connected with the energy and mass of the matter. And the movement of all the particles goes according to the curvature, and all that we have now is called general theory of relativity. So that's how it was developed, right? Riemann developed this at somewhere, I think it was 1854, so right in the middle of 19th century, right? And Einstein created his in 1916. So it was 60 years later. And now the whole physics is based on, believe it or not, on the curvature. But additionally to our dimensions like x, y, z, and t, right? Space-time, right? In modern physics we have more dimensions and more symmetries. And symmetries I just write for you, just modern theory of all fields. They are based on something like this. These are symmetries or groups, if you remember, and complex groups. This is three-dimensional groups, this is dimensions. Three-dimensional groups of rotations in three-dimensional complex space. Here is the same rotation as two-dimensional space, and here is one-dimensional space. So there are spaces that are somehow attached or affiliated, there are different terms for this, to the space-time point. Each space-time point can have not only rotations and shifts in space-time, but also symmetries here, that kind of symmetries, which describes all kind of force fields. What are these force fields? Just electromagnetic, right? Then so-called weak interactions and so-called strong interactions. And in addition, there's a gravity. So these four forces, four fundamental forces, they're based on space-time symmetries and these symmetries. And of course there are more dimensions. There are 3 dimensions more, 2 dimensions more, 1 dimension more, whatever. So what I mean that all is actually, mathematics of this is all connected with the Riemann spaces, actually Riemann space-times. Just for you to understand. And now what we have in quantum computers. Remember we're talking about entanglement, right? We have entanglement, again, this term. Entanglement. Entanglement means that each of these particles, each of these quanta are actually the same totally. It's just one. Another way of thinking about it, you can say that each quantum is connected with each and every other quantum directly. So this connected with this connected with this connected with this.
I'll make a hypercube.
Yeah, not hypercube. You know how much, okay, in the quantum computer modern, the most quantum computer are 10,000, right? So it's hypercube of how many dimensions? 10,000 particles, 10,000 qubits, right? You may say, you may think about hypercube, whatever. So it's definitely connected with these things. What I want to say that if you have more of them, in reality, each particle is connected with almost infinite other quantum. So we have the space-time of infinite dimensions. So this is what quantum computer is. It is a system of multi-dimension, lots of dimensions. In the modern computers, though, even these 10,000 elements, each of them has just 15 connections. So when we talk about hypercube, about like 7 to 8, something like this, right? 7 to 8 dimensions, not more. But the real things has infinite. Just we cannot implement it yet in the system, like computer. Interesting enough, another work for this, your dad should already know, Another name for such a system of connections, it is called neural networks.
Oh.
Because neurons in our brain are connected exactly like this. Each neuron have about 40,000 connections, not 15, 40,000. So the amount of dimensions in our brains.
So we're more complex than that computer.
Yes, of course. Brains are more complex. Yeah, brains are a very complex system. Yes, each of you have your own extremely powerful supercomputer in your brain, with a weight of just 1 kilo or less, right? So, and I want to just remind you just a little about this. When you have almost infinite dimensions, right? Remember, like in physics, we have how many dimensions? 4 dimensions plus additional dimensions, again something like 5. So we have about maybe 9 to 10 dimensions. That's it. Here we have infinite dimensions. So the quantum computer in perspective will have infinite dimensional system, and it can, remember this general cat? Like this absolute cat. So it can talk about very complex things. It can think about very complex things, and they are not numbers anymore. These computers are based on, first of all, they're not coded, they're not programmed. They're trained. They learn like people. Oh, sort of. They are more primitive than people, so but anyway. So they're trained. And they think not by regular logic, they think by associations. This is a human way of thinking. Right now, even your papa work with neural networks. Neural networks are coming more and more popular because they're very powerful.
There's a neural networks right here.
Yes, they're very powerful. They use them in translations, in thinking, in driving cars around. If you know this autopilot cars without pilotless cars, right?
Yeah.
They're all based on neural networks. All these systems are based on neural networks. Everything which is connected with the AI right now is moving to the neural networking. This is the modern way of doing things. So you will see a lot of these things there. And when quantum computers come to the real work, when they really can implement a quantum system as a network, as a neural network, the power of this thing will be very, 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 very huge. Very big. Okay, guys. So this is the end of this. And the only thing I want to tell, that in reality, okay, each quanta is connected with each other quanta. So all of quanta in our universe, and they're about 10 to the 80, right? To the power of 80. Remember? Quanta? Protons, neutrons, everything. They all interconnected. So this is about the amount of dimensions of this system, too. 10 with the 80 zeros. And qubits, again. There are qubits and dimensions. And how it looks like, in reality, I'll show you right now. Probably you've seen this picture.
That's the universe.
That looks like neural networks.
Yeah.
Yes, exactly. This is called so-called dark matter,
Which Peter knows all about.
Yeah.
and this is the map of, I would call it, informational highways net. You can see?
Well, because you have the picture.
Oh yeah. Just no problem. Just look at the picture. And our Earth, not Earth, but our supercluster of galactics, right? Our galactic. You see the mouse, right?
Yeah.
So it's somewhere here. It's called Virgo supercluster. Somewhere here. And there's some small spot here. So our universe is, so it is informational highways net, or whatever you may call it, quantum supercomputer with this power. Okay, this is enough for today. And I'm not going to do any exercises because you may I thought didn't even finish the previous ones. So, but there's no exercise on this. You may just think about it, talk with your papa and whatever.
I thought you were going to ask us to do
any questions?
Supercomputer 1 qubit.
Say it again. What?
I thought you were going to ask us for one a very simple quantum computer.
Okay, you may think about it. Very simple with 1 qubit. Yeah. You may think about you may think how it is possible. You actually know a lot already on paradoxes in mathematics, right? So we talk about this paradox, and you thought about this paradox one to many, right? One and many, and it's directly connected with this quantum thing. So so you may think how it may work in reality around us, right? And in our brains maybe. You may think about all these things, just connect A, B, and C and all these things, how they work together, and talk to your papa. And maybe the best question is just give me questions, like serious questions. Try to prepare like 3 big questions for me, okay?
Prepare 3 questions about quantum computers.
On this, yes, quantum, neural networks, universe, whatever.
Do you research?
Right
And
now?
come up. Not right now.
No, just homework.
Me, sir? What do you mean? You speak about quantum computers.
Come up with 3 questions.
3 questions. Just maybe you don't understand something, but try to make them really serious, okay?
And you 3 questions.
Yeah, that's right.
Yeah.
3 questions from 3 people.
And now, any questions for now? Do you have any questions for now?
Not yet.
Not yet. Okay, guys.
I
So
remembered why the number of algorithms is countable.
okay.
That's-
We will talk a
What I
little
said was
later.
right. It's not complete. Like the alphabet, the language is fine. The alphabet is finite.
Okay. Let's talk about it after off record. Okay. I'm finished recording, and then we can talk. Okay.